many open, nice open questions. So, I'm sure that all of you have encountered symmetries in optimization problems at some point. So, for example, it could happen in an optimization problem that if you swap the first variable with the second variable, you get an equivalent problem, and the same problem again. And therefore, if you're doing, for example, a branch and bound, it could happen that if you follow a path and you get into some subtree, then this subtree is equivalent as if you have followed a different path in which you permuted the values of x1 and x2, and you get a different another subtree which is equivalent, is symmetric to the first subtree, and therefore it's not worth to go through all of them. You're just losing time at the end of the day. So this is a phenomenon that happens quite often. So let's try to formalize this a little bit better. So what are symmetries in a nutshell? In a nutshell, symmetries are functions that leaves an object invariant. So for example, you have this nice picture by Escher. If you take it and you rotate it by 120 degrees, you see that you obtain the same picture once again. And therefore, the picture is left invariant by rotations of 120 degrees. Now, one kind of clear property that you have is that if you have two symmetries, two functions that leave an object invariant, and then you compose them, you again will get the same object. So if you look at the sets of functions that leave an object invariance, this set is closed under composition, and this is called the symmetry group of this object. And one particular kind of interesting set of groups which often appear in practice are groups that are formed, which are finite sets of linear isometries. An isometry is just a linear function, you can think as a matrix that preserves angles, right? So in particular, if you take the canonical basis and you apply some of these isometries to this canonical basis, you will get another orthonormal basis, right? And now we're interested in sets of isometries, let's say a set big G, which is closed under composition because we want that this set represents some group of isometries of some object. So this is the setting. A particular case of a group of isometries is a permutation group. And a permutation group is just an isometry that what it does is to permute the canonical basis, right? It just permutes them within each other. And therefore, if you have a permutation in this group and you apply it to some vector, what it does is just it permutes the coordinates, right? So this is quite often happening in MIPS. So when you're facing an optimization problem, and I here write in a very general form, let's say you're minimizing some function f subject to some specific feasibility region, we say that this problem is G invariant for some group of isometries G. If you take any feasible point and you take any group element and you apply the group element, this linear function to G, and then you get another feasible point. And the same when you apply G to X, the objective function is maintained. So this example in the right, for example, this linear optimization problem is invariant under the group that the only thing it does is, well, it contains the identity and the permutation of x1 and x2, let's say G, right? Which is just reflecting the space on this straight line over there. So there has been a lot of work in symmetry handling methods, well, in MIPS and in other areas too. In a very broad way, you could say that the literature separates itself in two big major techniques. One major technique is symmetry breaking inequalities, is how to generate inequalities that break the symmetries of your problem. And other methods that are a bit more specific to the specific algorithm that you're trying to use to solve your problem. Like, for example, you can look at your branch and bound tree and then in some way try to avoid symmetric subtrees. I won't go into details of each of these things, just but you can see them in the slide. One core concept when you're dealing with symmetries is the concept of orbits, or in some other way of saying is points that are equivalent to each other. Like, for example, if you have, again, this nice picture by Escher, and you look at some specific point X, maybe this here, which is the nose of this black fish here, you see that if I rotate this X by 120 degrees, I get another point, which is, again, the nose of this fish, which is kind of equivalent to the fish, right? And this other one here. And these 3 points are equivalent in some way. They represent the same information. So the set of points for a given X, the set of points that contains only points that are symmetric to this X, only points that you can construct as G of X for some G in your group, that's called the orbit, okay? And those are representing the symmetric points, points that are symmetric to X. Same in this optimization problem on the right, this polytope, I can take X, and this X is symmetric to the to this reflection around this straight line over there. Okay, so when you're dealing with breaking symmetries, what you're trying to do is somehow to select just one unique representative per orbit. Okay, that's in a nutshell what you're trying to do, and the definition I'm going to give you now, it goes into this direction. So we're talking about a fundamental domain. Fundamental domain, the objective is to break symmetries, and it's defined in the following way. We want to construct a closed and convex set. We want it to be closed and convex because we want to optimize over this set, right? So that's kind of a nice thing to have. And the first thing is that, first of all, we don't want to lose information. So we don't want to, F must contain at least one element for every possible orbit that we have of points in Rn, in our space. So otherwise we would lose information. And the other one is that we would like that this representative of each orbit is unique. We only, because this is the way we are actually breaking symmetries. But there is like an intrinsic difficulty that we cannot avoid having some orbits that have more than one representative, at least not in general. So what we can ask is that the representatives of the orbits that are in the interior of F are unique. For example, if I have an X here in the interior of this green set F, the orbit of X is somehow these 3 points that I guess are somewhere here. And then I have a unique representative of this orbit in F. But if I have this point X here in the boundary, then I cannot avoid having another element in the orbit that is also in F, right? So I have unique representations up to elements in the boundary. And in some way, well, 2 observations of this thing is that, okay, so this F helps you to break symmetries. And the other thing is that these are in some way minimal ways of breaking symmetries, in the sense that if you take a smaller set F, a smaller set, which is strictly contained in F, and it's also closed, this means that you will have some point which is in the interior of F that is not in this smaller set. And this means that this point won't be represented in F, won't have a representation, and therefore we're kind of losing information in some way. One point important to make is that in this case we only care about the group. We don't care about the optimization behind, the optimization problem behind. So we're kind of abstracting the optimization problem and just looking at the specific. The other observation is that if you take F and then you apply to F the group elements, in this case would be G, let's say G squared, if G is the rotation by 120 degrees. And this creates a tessellation of the space. This means that we will partition the space by these sets. And there we almost disjoint in the sense that they can only intersect in the boundary. So the first thing when you see this definition, the first thing you ask yourself is whether such an object always exists for any group of symmetries. And the short answer is yes. This is a quite old construction by Dirichlet. that, let me explain you the idea, which is quite simple to describe as follows. So let's take some vector alpha. Think about it as a direction in Rn, right? And now let's look at an orbit of some point. And now you would like to pick one, let's say you want to pick one element in this orbit. So one way of picking that element is saying, okay, I'm going to find the X I want to pick in my set, in my fundamental domain F, the element in the orbit that maximizes this function. Okay, so how do you do that? Well, you can add a bunch of constraints that says that X will be then in my fundamental domain if alpha transpose X is larger than alpha transpose GX. So the value of this linear function alpha is larger on X than any other elements on the orbit. Okay, and this actually defines a fundamental domain. You only just need to ask one specific property, is that this alpha has to be moved whenever you apply some element of the group that is not the identity. So, and well, I don't have time to go into more details, but this is a requirement that you have for this alpha. But it's not a very strong requirement in the sense that you can always find such an alpha. It always exists. One big disadvantage of this construction is that you need to add one inequality for each element in your group. And now, if your group of symmetries is very large, is of exponential size, for example, then you will have a fundamental domain with exponential many inequalities, and things are even more worse than that. I mean, because you cannot even separate them, as I will mention later. So this Dirichlet fundamental domain does the job in some way, but it has this big drawback that it's hard to handle. So as I said, like the first, I want to talk a little bit about the motivations for studying these fundamental domains. So the first motivation, as I said, is breaking symmetries, for example, in MIPS, right? So you when you have an optimization problem, let's say this one that is G invariant, and you can have a fundamental domain for this group, then you can, instead of optimizing over X, you can optimize over X intersected with the fundamental domain. This breaks symmetries, but as you maintain one representative per orbit, you don't change your objective function, right? So in this small example here, F can be like this half space up there, and then you can intersect with this half space and you don't lose it. Maybe I'm a bit behind schedule, so I won't go into very much details, but this same problem appears in a bunch of other settings, not only in MIPS. Okay, so if you look at a little bit in the literature, for example, I encourage you to look at this paper from this year, very recent, that deals which asks a lot of questions about symmetries in the context of learning, for example. And in learning, you have a lot of non-convex problems in which this type of things seems to have a lot of possible applications. One, and I will talk about another motivation later, but first of all, when you're breaking symmetries then, and trying to use these fundamental domains, there's, I would say, two major difficulties to see what you can achieve or you cannot achieve. First of all, as I said, is that in general, fundamental domains can be hard to separate, even for the most, like, I would say, useful cases. For example, when you have permutation groups, which appear very often. And in that case, a general Dirichlet domain in general can be hard to separate. So that already is a problem, and in general can have exponential number of facets. Now, the good thing is that there are many, in principle, there are many ways of constructing fundamental domains. So even if this particular Dirichlet domain is hard to handle, it doesn't mean that all other fundamental domains are hard to handle. So then the question is, okay, so what type of, how can I construct other fundamental domains that have, like, behave better from a computational perspective, right? And the other problem is that if this problem that you might have orbits that are overrepresented, for which you are breaking symmetries in a, like you are almost not breaking symmetries, or breaking symmetries in a very weak way, if you want. Okay, so and for example, we can construct this example, which is not that complicated, for which you have a very natural fundamental domain with nice properties, like with a small number of facets, for example. But if you look at binary points, then there could be orbits of these binary points that are very overrepresented in the fundamental domain. So the intersection of the orbit with the fundamental domain can be exponentially large. So in some way, for these points, your symmetry breaking possibilities is really weak. And if just by coincidence, your points, the points that you care about, are in those orbits, then your symmetry breaking capability of this fundamental domain is very weak, and you're not doing much by adding these extra constraints. Okay, so that's a little bit the challenges in terms of fundamental domains when you're dealing with symmetry breaking. But there's a third motivation which I like a lot, that I wanted to mention, which is well, it's given by, for example, by this paper by Kaibel and Pashkovich, like from 10 years ago, that says the following. Let's say you have a polytope, which is G invariant for some group G. But G is not any group. Let's say it's a reflection group. A reflection group is just a group which is generated by reflections. A reflection means just you take a hyperplane and then you reflect the space around this hyperplane. So for example, this hexagon, you can reflect it around any of these straight lines, and you get the same hexagon again. And then you can also obviously compose different reflections, and then you get the whole group of symmetries of this hexagon. So it's not hard to show. And then you take F to be some fundamental domain for this group G. And then they say the following. If you want, you can find an extended formulation for this polytope P by looking at an extended formulation of P inter F. So let's say, for example, in this particular case, that F is this little cone over here. This is F. And P inter F is just this triangle, right? So it's a very simple object. In this case, at least, in this small example of the hexagon, or any n-gon, it would be the same. And then the extended formulation of, you can get an extended formulation of your whole polytope by adding some extra overhead inequalities, which is, the overhead is quite small. It's like, depending on n, which is the dimension, and this parameter that tells somehow how complicated is the group. Okay, I don't want to get into the specific details. But what I like about this thing is that you start with a polytope that had lots of symmetries, let's say, and then you can get a much compact or nicer description by understanding the symmetries. So in some way, the symmetries are giving you a way of simplifying the polytope. And this is a point of view that is which I find which is very nice. That it's not like in MIPS we are usually like scared of symmetries in some way, or that we need to deal with them, like they provoke a problem. But in this result, actually symmetries help you simplify an object. So it's something good for you in some way. Okay. One very important observation is that for reflection groups, the fundamental domains tend to be very simple in the sense that they're unique. There are not many ways of defining a fundamental domain. It's essentially unique up to applying elements of the group of F. So here, for example, the F is not unique because obviously you have another fundamental domain here, right? But this is just some GF, or some G. So fundamental domains are equal. So if you would like to, for example, try to generalize this thing for other groups that are not reflection groups, you probably would need to specify what type of fundamental domain you're considering if you want to generalize this. And this is a nice direction, I think. Okay, I don't have so much time. I wanted to tell you a little bit about some geometric properties of fundamental domains, specifically of the facets, because we also have like several open problems there. And I think that they are very fundamental questions in the sense that they could help you understand what type of fundamental domains could we hope to construct, and what are the limitations of these fundamental domains. Okay, so the first observation when you try to study the facet description of a fundamental domain is that whenever you have a fundamental domain F, like let's say this is the set here, and then you apply some group element, then you get some kind of copy of GF, which is rotated or like reflected, something like this, right? This is not intersecting except for the boundary. So since these two guys are convex sets, I can separate it by some hyperplane, let's say G of H. So for every G, there is a hyperplane that separates F from GF. So one relatively easy thing to see is that the fundamental domain is just the intersection of all the semi-spaces that are defined by these hyperplanes, right? That's kind of, and you can say a bit more about this. For example, if you look at the G's that actually define facets here in this description, those generate the group and structural things like this. But a bit more interesting, and I'm really running out of time, so I hesitate. Okay, I will go very fast on this. A very kind of fascinating meta question is what type of inequalities can actually define a facet of a fundamental domain for a given group. And if you want to talk about a specific question here, you could think, you can ask yourself whether you can construct a facet that looks or not equal or in the same way as the facet that the Dirichlet domain look like, right? And the facet of the Dirichlet domain look like this, right? So maybe for every G that defines a facet, you can find some alpha that gives you that this is the facet of your fundamental domain. So there's a nice geometric characterization of this, which maybe I will just skip. And I will just say very briefly because I ran out of time. The main let's say conclusion of this is that we cannot say this in general. We need to add some extra hypothesis on the fundamental domain to say that every facet defining inequality is of this type. But we don't know whether you actually need this hypothesis or not. Okay, so this is also a nice open problem. It would be nice to say that all the facets ever appear in a fundamental domain of Dirichlet type, because this gives you a boundary of what you can or cannot construct as a fundamental domain. Okay, and also very briefly, one of the main results we have in this IPCO paper was that you can construct we can generalize somehow the idea of the Dirichlet domain and give a general construction, a little bit inspired by these geometric properties that we derived in the previous slide. I won't go into the details, but in a nutshell, with this kind of general method, we can construct all the fundamental domains that we have found on the literature so far, at least. In particular, we can construct what is called the Schreier-Sim inequalities, which were introduced by Liberty and Ostrowski, and also by Salvagnin a few years ago. And in particular, we can show that for permutation groups, we can construct a fundamental domain which has only a linear number of facets. Okay, so permutation groups are kind of nice in that regard. Now, the problem is that this fundamental domain, which has very few facets, behaves very bad for binary points. So specifically for this type of fundamental domain, you might have that binary points are really overrepresented. So you might have like an intersection. One particular orbit can intersect F in an exponential number of points, and this is bad for symmetry breaking in a way. So we have plenty of open questions, based on this last thing that I mentioned, one very nice natural question is that if we're looking at permutation groups, like, can you find a fundamental domain that has these two nice properties? One that has polynomially many facets, or at least that you can separate it in polytime, but the number of representatives of binary orbits is small. For example, constant. I mean, it could be just one. That's kind of the ideal case, but it would be already nice if it's a constant or even a polynomial number. But avoid like this exponential behavior. This is very unclear, and I like a lot this other question that I mentioned about the geometry, because this kind of puts you, as I said, like the limitations of what you can do or not do with fundamental domains, and probably answering that question might help answering also this one. There is a bunch of other questions. Many of them I already mentioned, so maybe I will just finish it up here and then leave a little bit of time for questions.
Thank you, Jose. Thanks for the great talk. Do we have any questions for Jose? I actually had one, but it's not now included in the open questions. So
I also have one, Jose. This is Yuri.
Yeah. Yes, Yuri, please.
So yeah, about the extended formulation question. So you can see Kaibel and Paskovich construction as the generalization of this construction by Bental and Nemirovsky, which essentially they used to give a polyhedral approximation of the second order cone. And Kaibel and Paskovich, they take this and they generalize it. So I think I have a very vague question, which is, do you think the nonlinearity in the extended formulation can help somehow in getting good extended formulation? Do you have an intuition of why it may or may not help?
The short question is I have no idea. I have no idea. Yeah, I mean, I was aware about this second order cone, but I never really thought about this in this way. So I don't know.